with torsion coefficients, well, I can just take with mod L coefficients. And from the perspective of having the Hecke action on it, and sort of from the perspective of what systems of Hecke eigenvalues can occur in what degrees. So this is a product of restricted product of spherical Hecke algebras at all but finitely many unramified primes. And the expectation is that this cohomology is somehow degenerate outside the middle degree. So the cohomology occurs in the range from 0 to twice the dimension, but the expectation is that what you see in cohomology outside the middle degree D is somehow degenerate. And to make it more precise, I'm going to say, well, okay, so you can put some local conditions, but for what I want to do, and for applications, it's better to think about it from a global point of view. And so that's why I have a global Hecke algebra here. And in order to formulate what kind of degeneracy condition I want to look at, I'm going to take some maximal ideal in the support. So let M inside here be a maximal ideal that is in the support of, well, of one of these cohomology groups. And then, so the first thing is that in this setting, there is a Galois representation, so a global Langlands parameter associated to this. So this maximal ideal represents a system of Hecke eigenvalues, and associated to it, you can find a global continuous and semi-simple representation of the absolute Galois group of F. And this is a 2n-dimensional mod L representation valued in some finite extension of FL. I just put FL bar for simplicity. Okay, so this is continuous and semi-simple, and it has the property that it's characterized by what it is on the Frobenius elements at unramified primes, and there the characteristic polynomial can be written explicitly in terms of, I guess, the eigenvalues that come from the system of Hecke eigenvalues. And so people say that the Frobenius eigenvalues at unramified primes of this global Galois representation match the Satake parameters of M. And so in this setting, this is quite subtle. So you could, in principle, have classes in cohomology that don't lift to characteristic 0. And so it's not clear how to construct something like this. But this is one of the key ingredients in this work of Schulte that I mentioned yesterday, which is about constructing Galois representations for torsion, even in the cohomology of locally symmetric spaces that are not Shimura varieties. So his argument goes via looking at these kinds of unitary Shimura varieties and showing that even for any mod L class, possibly something that's torsion, it still can lift to characteristic 0. So it's congruent to something in characteristic 0 that we understand, and then there is an associated Galois representation.
Just to be clear about the definitions, that's what you would call non-degenerate. The degenerate is not something.
Well, I haven't said anything about it yet.
Yeah.
So this could be degenerate or it could be non-degenerate. I'm just saying that the way that we want to characterize things. But yes, I mean, you're right in the end that what we'll see is that under an appropriate condition on this Galois representation, you can show that this is concentrated in degree D, and then in particular, you also deduce that it lifts to characteristic 0. But for now, all I've said is that anything that you see in here, any system of eigenvalues that you see in here, whether it's degenerate or not, it will have some Galois representation attached to it. And that's constructed by congruences. Okay, and so, I mean, the actual conjecture I could state here is due to Emerton and also to Caligari-Garrity. And the conjecture is that if this representation is irreducible, or if I take it valued in some finite extension, absolutely irreducible, if this happens, then this should be in the middle degree. So there is this kind of conjecture where you put a global condition. The global condition is that the associated parameter is irreducible. If rho m bar is absolutely irreducible, then hi of this with mod L coefficients localized at M is only non-zero if I is equal to the middle degree D. Okay, so this is one conjecture. I guess you can check it by hand in the case of modular curves. It can be proved in some other small dimensional examples, but for the most part, we're not quite at the point of knowing this. But then what happened in the past 10 years, let me try, is that instead people started putting local conditions on this Galois representation. So restricting to the decomposition group at some prime and putting some local condition there and getting some results about degrees of cohomology under this local condition. And so I've kind of just compiled in one theorem the results that are now known for these unitary Shimura varieties. Oh, and I'll mention one thing, which is that this Shimura variety is non-compact. So you can ask the same kind of questions for cohomology with compact support. So this, so the first result towards this was in 2019, and this was good enough for applications, but then there were better results proved in subsequent years. So Koshikawa removed quite a few of our technical assumptions and also gave a different proof in 2021. And then last year, there's a paper of Hamann and Lee that introduced an even more general method and also proved a more general result. And so I'll say here, first vaguely, if rho m, say, restricted to the decomposition group, well, let me just say it. If rho m is sufficiently generic, at some auxiliary prime, right? So that means you want to decompose, you want to restrict to the decomposition group at each prime above P and put some condition there. Then, well, you don't quite get that the cohomology is in the middle degree, but you do get that the usual cohomology is in the degree, in the middle degree and above. So this is only non-zero if I is greater than or equal to D. And then the dual statement also holds true. So the cohomology with compact support is in the middle degree and below. And if you put yourself in a condition, so if this rho m bar is irreducible, so if the global representation is irreducible, and also you have this genericity at some auxiliary prime, well, then these two agree, and then the conditions tell you that it really is in the middle degree. But the theorem also applies to things that are globally reducible. And in fact, sort of that's the the interesting case for the application to modularity is that you want to actually consider something where the representation has two factors. So it's a direct sum of two irreducible n-dimensional representations. So I'll come back to that, I guess, in the next lecture. But I want to give you tell you what the condition is in the various works on this. So first, in the setting of the first two papers, the genericity condition is that, first of all, P has to split completely in S. And then you need that for any V dividing P, a prime of F, rho m bar restricted to this is unramified. I mean, you need this is not a strong condition because somehow there will be, if there's one prime that works, there will be infinitely many. So you can always assume that you're unramified. But the point is that the eigenvalues of Frobenius, so alpha 1 through alpha 2n, are the eigenvalues of Frobenius at this place. You need that alpha I over alpha j is not equal to P or P inverse if I is different from j. So basically, you want there to not be two eigenvalues that differ by P. And the reason for that is essentially that you want to make sure that any lift to characteristic 0 of this representation somehow has trivial monodromy. Turns out this is a useful thing. So what will happen, in fact, is that any lift to characteristic 0 of this will correspond under the local Langlands correspondence to a generic principal series representation. And yeah, it turns out this is a good condition to work with. I guess you'll see where it comes up a little bit later. But I just wanted to make it very concrete for you and also to tell you what the consequence is. So essentially, on the side of representations of GLN of FB, you want to see irreducible principal series. Okay. And so this latest paper of Hamann and Lee actually goes significantly beyond this because they don't need the prime to split completely in F anymore. And this is something that, I really sort of didn't know how to do, is how to prove such a result without this assumption. And you'll see why there's really a significant difference on the level of the geometry. So in the setting of Hamann and Lee, what you need for now is just P is unramified in F. And in fact, there is a small condition, but I forget it right now. So there's a small condition that you want every prime above P to split from F plus to F, but only if n is odd or if n is even, and I forget which one it is right now. And you want, so you look at, again, the same eigenvalues of the Frobenius at every V dividing P. And now you want this to not be in, here I made a mistake in my notes. So you don't want it to be the residue field cardinality at V or its inverse, and you don't want the ratio to be 1 either. So slightly stronger condition on the level of the eigenvalues. But in practice for applications that this doesn't matter very much. And in fact, it's sort of much more significant that you no longer have to impose that the prime is split completely. Okay, and the other thing is that So both Koshikawa and Hamann and Lee can actually formulate their theorem without having to work with a global system of eigenvalues or with a global Langlands parameter. They can just localize at the system of eigenvalues at P. But for what we're going to use this theorem for next in the next talk, we need a global Galois representation anyway. So by localizing at some maximal ideal that is just inside the Hecke algebra at P, and this is just, I take this to be the product of the spherical Hecke algebras at the primes V dividing P of F. Okay. And I want to mention some related results. So kind of the first version of this theorem was really proved in 2015 for compact unitary Shimura varieties. Oh, and before this, there's also work of Boyer that applies to Harris-Taylor Shimura varieties and that uses a completely different method. So let's see. So actually, the first thing I should say is Boyer, because his paper was the first to appear, I think also in 2015. And so this is in the Harris-Taylor case. So these are unitary Shimura varieties with a specific signature, 1 n minus 1, and also compact. So 1 n minus 1 at one infinite place and 0 n at all the others. These are the Shimura varieties that played an important role in the proof of local Langlands for GLN due to Harris and Taylor. So the geometric proof. There's work of myself and Matteo Camiozzo in the Hilbert case. So for Hilbert modular varieties, but with this kind of condition here rather than this. But well, there's work of my PhD student, Mafalda Santos. So I guess what happened is that in 2019, Schultz and I really worked with only these quasi-split unitary group Shimura varieties. And then Koshikawa introduced a general method, but this didn't quite apply to all PL type A, so all unitary Shimura varieties. It applied to all compact ones, and then there was some missing ingredient in non-compact cases. And so my PhD student, Mafalda Santos, provided this missing ingredient, and then she proved a version of Koshikawa's theorem that applies to all PEL type A Shimura varieties. And then, I mean, the important thing is this paper of Hamann and Lee actually treats more cases. So it doesn't specifically work with these ones, but really treats a more general class of Shimura varieties. In particular, it applies to Siegel modular threefolds. And the point is that, well, they introduce a robust argument, but they really need to know that the classical local Langlands correspondence for the group at P, or well, the group at each prime V above P, that this classical local Langlands is compatible with the semi-simple correspondence of Farg and Schulze. So that's kind of one thing. Like they work with basically PL Shimura varieties and also some cases of abelian type Shimura varieties, and they have some maybe extra restrictions on L, but the key thing is that they need to make use of this compatibility. So if one can get this compatibility more generally, then the method should also provide more general results. Just had local Langlands correspondence there. And there's upcoming work, I think maybe not available yet, of Daniels, Van Hoft and Kim, and Zhang, Mingjia Zhang, that treats certain inner forms of GSB4. And somehow the point there is they take the method of Hamann and Lee, but they refine the geometric ingredients that are used to apply to Shimura varieties of Hodge type. And then again, they need this compatibility between Fark-Schulze and classical local Langland, but they can, get some more general Shimura varieties in this setting. I think those still only compact for now on. So inner forms that give rise to compact Shimura varieties for now. Okay, and so I'll talk about applications in the next talk. Maybe, maybe now is a good time to pause and ask if there are any questions about the statement of the theorem, or like the general, I don't know, general area. So the rest of the talk, I will discuss sort of the things that go into the various proofs of this theorem and how the different proofs can be combined to give some information also about local global compatibility. So the strategy of proof, well, there are, and so Boyer, I said, just uses a different method. So he really works with integral models of these Shimura varieties. But outside of his work, pretty much everything else uses the geometry of the Hodge tape period morphism. So that's a key ingredient. And so this is something that has now been really clarified due to Mingjia Zhang's PhD thesis. And so that's, I think, the right perspective on the geometry of this morphism. And then the other thing to say is, so originally my method with Schulze used the trace formula to compute the cohomology of certain Igusa varieties. And in particular, work of Sagu Shin on writing a stable trace formula for these Igusa varieties. And then this has now been replaced first by Koshikawa and then by Hamann and Lee with an argument that really uses ideas from geometric Langlands. Replaced by, anyway. So I guess really using the work of Fark-Schulze and then further ideas from geometric Langlands to understand, I guess, the cohomology of Igusa varieties, or more generally, the cohomology of the relative Igusa stack of Mingjia Zhang. Okay, so I'll say more about this now. Maybe I erase these boards. And then we start actually discussing what goes into understanding this cohomology. All right. So to get to the Hodge tape period morphism, the first thing that we are going to do is pass to adic spaces. So instead of Betty cohomology, I'm really going to look at the Étale cohomology of the Shimura varieties considered as adic spaces And I can base change to the completion of an algebraic closure of QP. And I want to pass to an infinite level at P. And so I just want to work with a tame level, K away from P. And then, so, okay, I could spend a lot of time on history, but let me tell you the state of the art first. So this is a theorem of Zhang's PhD thesis, so from last year. There is a Cartesian diagram of small v sets. You don't have to worry necessarily about this, what this means, but it's something in kind of the world of diamonds. But we're looking at the Shimura variety with infinite level at P. So this is a perfectoid space. And this has a Hodge-Tate period morphism to a flag variety. And this flag variety, well, it's the adic space just attached to the flag variety that corresponds to the Siegel parabolic, or like the parabolic cut out by the Hodge co-character of the Shimura datum. So this is pi Hodge-Tate. And then, okay, so it was already known that there is a map from the Hodge-Tate period domain to Bungie. Maybe this map is sometimes called the Beauville-Laszlo map. So somehow the idea is that there's some, well, you can kind of construct a universal family of G bundles on the far content curve that on the relative far content curve over the flag variety. That's what gives this map. And it's a map that is L cohomologically smooth. So if I quotient out by the level at P, it's L cohomologically smooth. So it's not too bad, I guess, as a map. And then, so what Mingjia did is she filled in this diagram and constructed an Igusa stack so that you really have a Cartesian square. And maybe I will call this, so she calls this pi Hodge-Tate bar. I'll just call it pi bar for the rest of the talk. And the point of this is that, well, okay, so one thing is that the fibers here are perfectoid Igusa varieties. And so they are of the form ig B over our perfectoid field C, where B is an element of the Kottwitz set for G, and it's bounded by the Hodge co-character mu. So this Igusa stack kind of lives over just a minuscule part of Bungie, the part that's bounded by mu. Okay, so what can I don't know. I don't know how much people know about this or don't. So this is kind of, in some sense, a culmination of a story that started 20 years ago with Montauban's PhD thesis. So there she described Newton strata inside integral models of Shimura varieties by showing that they have a cover by a product of two things. So one of those was a Rappaport zinc space, so a local analog of a Shimura variety. And the other one was kind of an object of a semi-global nature that's a so-called Igusa variety. And in fact, okay, I should say that the Igusa varieties really go back to Igusa curves that cover the ordinary locus inside the modular curve. And in this generality, they were first studied by Harris and Taylor in this book on local Langlands for GLN. But then sort of generalized to the PEL case in Montauban's PhD thesis. So I guess this, yeah, provides, I don't know, generalization maybe, or like I don't even know what to call it. Well, let's say a vast generalization of the so-called Montauban product formula. And so, there's like a very nice thing that you can understand moduli theoretically, thinking about, the special fiber of the Shimura variety or like the, and then I guess I should say, and sort of infinite level version. So about, I guess, 10 years ago in my first paper with Schulze, we provided an infinite level version of this one-to-one product formula, where essentially, well, we analyzed the fibers of this Hodge-Tate period morphism, and we showed that the fibers over a Newton stratum corresponding to B were these Igusa varieties for B. And in fact, we also proved a product formula at infinite level. But the difference is that, well, our product formula was really for a fixed B. Whereas Zhang's PhD thesis works over bungee, so allows B to vary kind of very nicely. And I think that this is a really important result for the study of Shimura varieties, because it provides a lot of extra structure that was not available before. And for us, maybe the most important thing is that for certain nice sheaves on bungee, there are excursion operators constructed by Farg and Schulze that act on them. And one can exploit this extra structure, so the sort of spectral action of Farg and Schulze. And that's something that was not available before, and I guess isn't available if you just kind of look, think about Igusa varieties from the more classical perspective. And so that's one way in which the Igusa stack is very significant. Okay, so do it like this.
So in particular, this diagram somehow gives the link to geometric Langlands. And
yes, this diagram is also the link to geometric Langlands. That's right. And so I wanted to look at the cohomology with FL coefficients of the Shimura variety. And let's say we're looking at the cohomology at infinite level, because you can always descend afterwards. And then the point is that because of this Cartesian diagram, you can really, well, it's better to look at the relative cohomology of the Igusa stack. And so I can define two sheaves. So I'll define an F lower shriek and an F lower star. F lower shriek, I take R pi bar lower shriek of FL. And F lower star is R pi bar lower star. And sort of point-wise, so the stalks of these sheaves just give you the cohomology of Igusa varieties. So here the stalks are certain cohomology of Igusa varieties, but with compact support towards the boundary. So basically you can construct a partial minimal compactification of Igusa varieties and take a lower shriek functor from the open Igusa variety to this partial compactification. And that's what this cohomology is here. And here, the stalks are just usual cohomology.
Right, this I is the lower map in the diagram.
Yeah, it's the lower map of the diagram. But the point is that there is a base change result. It tells you that you can compute the lower map in the diagram. And then you can, well, basically, I guess to understand this here, this is the same as pulling back what you see here. And so you're also at the same time computing the relative cohomology of the Shimura variety over the Hodge-Tate period domain. And so it's either the cohomology with compact support or the usual cohomology. But so pi bar is this lower map here. But given that you have a Cartesian diagram, you have a base change result that tells you that you're also computing this. And I guess this is an intermediate step towards computing the full cohomology of the Shimura variety. Okay, and these are representations of, and here maybe I was a bit rushed. So I've still fixed my tame level. So here I'm taking the Igusa stack with some fixed choice of tame level. They behave kind of like Shimura varieties. So, you know, there's Hecke correspondences away from P and all that. Okay, and these are complexes of smooth representations of a certain twisted Levy subgroup of the group G. Sorry, let me think for a second. Yeah, maybe I do G. I do something like this. And in fact, they have admissible cohomology. Because ultimately you can relate this to Igusa varieties that are just schemes of finite type over a finite field. So you can compare the cohomology of perfectoid Igusa varieties with the cohomology of more classical ones. And for this reason, these live in the very nice category of sheaves on Bungie that Farg and Schulze consider. So this is so-called ULA sheaves. This is a category considered by Farg and Schulze, and they give various equivalent definitions. The definition that I want to use is just that sort of pointwise for each B in B of G, the stalk of the sheaf has to be a complex with admissible cohomology. And then it's easy to see that the relative cohomology of the Igusa stack does give you something in this category. Okay. Right, and then the upshot is that we can make use. So here we have spectral action constructed by Farg-Schulze. And the only way we're going to use it for now is to localize at a semi-simple Langlands parameter at P. And I mean, in practice, this is going to be a collection of Langlands parameters at all the primes V dividing P of F. I'm kind of thinking of my group over QP via the Bay restriction of scalars. So there's an appendix to the paper of Hamann and Lee due to David Hansen, where he explains how you can construct this localization and how it behaves. And the point is it behaves very nicely. And if I localize this sheaf at this Langlands parameter, then somehow any irreducible subquotient that I see in there will have semi-simple local Langlands parameter equal to phi p. So it picks out the part of one of these sheaves that has that Langlands parameter. And it's a direct summand of the original object. Okay, so
Sorry, could you
Yeah.
explain that a bit more? What does it mean to localize at the Langlands?
I don't want to go into this. You can look at this article of Hansen. Sorry, I'm not going to go into this right now. But it just means that you can decompose your object as a direct sum over local Langlands parameters such that, right, so I can write this one as a direct sum like this over local Langlands parameters at P. And I take the direct summand corresponding to this one. So it uses this action of excursion operators that's constructed by Farg and Schulze. Okay, so. I want to now tell you how to prove the theorem and also how to get something towards local global compatibility. All right, so, and I have to tell you one more thing before I can explain the proof of the theorem. Namely, there is a perverse T structure on bun G that is defined with respect to the Newton stratification on it. So this bun G is a disjoint union of strata indexed by elements of the Kottwitz set. And each of these strata can really be identified with a classifying stack. So each of these with a classifying stack of some kind of thickening, some pro-unipotent thickening of the group GB. So GB is a twisted Levy subgroup of G. So it's in fact an inner form of some Levy of G. And there's some pro-unipotent thickening in the category of diamonds, that's GB tilde. And for the most part, you can ignore the tilde when you're talking about local Langlands or when you're talking about cohomology with mod L coefficients, and L is different from P. What it does is it gives you a degree shift on cohomology, but it doesn't do much more than that in this setting. Okay, so you have these strata, and you can define a perverse T structure. Basically, I guess you look at the dimension of these strata and you can define T structures on each of these, and then you can glue them. And what I want to say is that these sheaves are both semi-perverse from this point of view. So the first kind of ingredient in the proof of the theorem is that F lower shriek is, actually don't know, is this called upper semi-perverse or lower semi-perverse? Anyway, it's in perverse degree less than or equal to 0 with respect to this. So this is proved using, so it ends up, this condition, it just ends up being a condition on the cohomology of the strata needs to be in a certain degree and below. And sorry, the cohomology on each stratum, which is the cohomology of these Igusa varieties, needs to be in a certain degree and below. And it turns out that this can be proved using Artin vanishing for the partial minimal convectifications of Igusa varieties. So this is the cohomology of the partial minimal convectification with coefficients in some J lower shriek of FL. And this partial minimal convectification is affine. So using Artin vanishing. Sorry?
If a compactification is affine, it's kind of far away from being compactifying. So
this, which are affine.
but of course you're happy because you have Artin vanishing.
So, okay, so you believe that once you know these are affine, you get some bound, and you can apply it to that. And I claim that degrees really add up to give you the result you want to show that this is in perverse degree less than or equal to 0. The question is, why are these affine? I mean, you should think, for instance, in the case of the ordinary locus on the modular curve, right? That's affine. And the Gustav variety is just a cover of this. I guess in the modular curve case, it's really, yeah, I mean, well, they're, I guess, profinite covers. And so this affineness carries over.
What do you mean by partial compactification?
Well, it means that I want to compactify towards the boundary of the Shimura variety. I don't want to compactify towards interior Newton strata, right? So I can have, if I have B, then there's this Bruhat ordering, and I have like degeneration. Like I can compare two different B's. So for example, you know, you can have an ordinary family that degenerates to something super singular, but I don't want to look at that. I want to look at the compactification just towards the boundary of the Shimura variety. And so for the ordinary locus, the partial compactification would be adding in the cusps, but not adding in the super singular points. So that would be for the modular curve. And so ultimately, the affineness comes from this, from the fact that the ordinary locus is affine. I mean, you can prove affineness of central leaves, of partial minimal compactifications of central leaves, by relating them to partial minimal compactifications of Ekedal Oort strata, which are then proved to be affine using Hasse invariance. So I guess this is something that was done in this paper with Schulze from 2019, and then generalized in the PL case by my PhD student, Mafalda Santos. And then I think there's a very general result due to a student of Kai Wen Lan, maybe applies to Hodge type, that proves this. I forget the name of the student, unfortunately, sorry. Okay, so
Are you considering this as a scheme now? Like, was there some algebraization of this partial?
so you can always compare it, right? So these perfectoid Gustav varieties are kind of obtained by taking adic generic fiber of the Witt vectors applied to the perfect object. And sort of the original object is algebraic, I guess is really a finite type. You can look at the perfection, take Witt vector slit, take adic generic fiber, and then that's the other thing. So yes, I'm kind of confusing whether I'm on the adic generic fiber or on the special fiber, but you can compare the cohomology basically. So there's a very general, result for comparing cohomology in this kind of setting.
Cool, thanks.
Right, but actually, yeah, that's a good question because you know, Artin vanishing isn't known for affinoid perfectoid spaces, but you can relate it to something where you do know it. Okay, and this is in perverse degree greater than or equal to 0 by duality. And sorry, I think I'm running out of time, so I think I won't be able to tell you about local global compatibility, but I can at least tell you how the theorem is proved. So how about that? So that's the first thing, the first observation. The second observation is that, well, I guess you need to actually use the genericity condition in some way in order to cut down these sheaves. And I guess the most general thing that we know now is due to Hamann and Lee, and also originates in a previous paper of Hamann. So the previous paper is called something like Geometric Eisenstein Series for the Far Content Curve. And so this is a really key ingredient in their work. Prove that if phi p is sufficiently generic, then, so the second key ingredient is, so I can look at the whole category of ULA sheaves on Bungie, and I localize it at a sufficiently generic parameter. And then what they prove is that this just breaks up as a direct sum over elements in B of G that are so-called unramified. And that's where the group GB is actually an inner form of G rather than just an inner form of the levy of G. And of just the corresponding category over that point. And so here, the corresponding category is the category of complexes with admissible cohomology of GBQP and with model coefficients, and again, localized at this param. So this is saying that if you're strictly looking at one such sheaf, but where every subquotient has Langland's parameter that is sufficiently generic, then the sheaf, like there are no extensions. The sheaf is sort of as simple as you could possibly hope. First of all, it's only supported on the so-called unramified elements of B of G. And then, you might expect to have a semi-orthogonal decomposition or something like this, but in fact, it's just really a direct sum. Okay, and remember, right, our F lower shriek localized at B and F lower star localized at B are in this category, right? There are elements here. And so they break up like this. So this is saying that, I guess that these are even just supported on the unramified elements that are bounded by mu. Okay, so the next thing, I can make this big. The next thing is that so if P splits completely, so this was the original setting of my work with Schulze and also of this paper of Koshikawa, then the elements that are in BG but bounded by mu and that are also unramified, well, there's only one of them. It's the ordinary. So that's the case where you have a non-zero, non-trivial ordinary locus, and that's the only unramified element. And so already from 1 and 2, you're basically at the point of proving the theorem in this split case. Because from 2, you know that, say, both of these are really only supported on the ordinary locus. And then, well, okay, so this is still just for the relative cohomology of the Igusa stack. So you can ask about the cohomology of the Shimura variety. But in this case, the ordinary locus is just parabolically induced. So to recover the cohomology of the Shimura variety, it's just a parabolic induction. This is exact and it doesn't produce more degrees of cohomology. And so you get the right inequalities just by knowing it's supported on the ordinary locus, and you can compute the cohomology of that by hand. Okay, so that's very easy with these sophisticated methods, but also, so if he doesn't split completely, but is merely unramified, then you do really have more elements in here. And then it can be that for some of them, when you look at the cohomology of the Shimura variety, what you have is kind of basically to feed this into a cohomology of the Rappaport-Zink space. And that could a priori produce more cohomological degrees. So even if you start out with some perversity and you know some bound here, it may be that when you kind of feed it into the cohomology of the Rappaport-Zink space, this spreads out the degrees. But so that's the third thing that Hamann and Lee prove. So what happens to actually recover the cohomology of the Shimura variety is you have to apply a Heck operator, essentially. And so that's where the idea from geometric Langlands comes in. So it's the Heck operator corresponding to the Hodge co-character mu. And this is reverse P exact on this subcategory localized at a generic, efficiently generic at phi p. Okay, and then with this, you're really done in general. Okay, so maybe just in 1 minute, I can tell you in words how you can sort of combine the different approaches. So the other thing, well, maybe I'll write this down. This is a separate thing, just proved in this paper of Hamann on geometric Eisenstein series. It's a purely local statement. He shows that there exists a Hecke eigensheaf on bond G with parameter Pp. Basically writes down a formula for it because it's in this category. So it's just a direct sum of its restrictions to the unramified elements. And he writes down what representation you should have there and verifies that this satisfies the Hecke eigensheaf property. This is something that was conjectured by Farg sort of about almost 10 years ago when he first sort of started thinking about geometrization. And so one thing that Lingjia Zhang and I are working on now is showing that at least in this sufficiently generic case, it's not just that you can, that you can prove that the cohomology is in 1 degree, but you can actually really compute these sheaves. So for example, if you localize in addition at a non-Eisenstein maximal ideal, then you can show that these two sheaves agree. So somehow non-Eisenstein means you get rid of cohomology from the boundary. And so that means that cohomology with compact support agrees with usual cohomology. And then you combine the two semi-perversities to get really a perverse sheaf. And then you have this decomposition. So you know this perverse sheaf is just a direct sum of sheaves supported on these unramified strata. Because of perversity, they are supported in 1 degree. And then the original method that was used in my work with Schulze actually computes what this cohomology in 1 degree is, at least on the level of the Grothendieck group. And then it exactly agrees up to some multiplicity with the local Hecke eigensheaf that was constructed in the paper of Hamann. Okay, so I'll stop here.